There's a particular kind of stillness that happens just before sleep. Not the stillness of comfort, but the other kind. The kind where your body has stopped moving, but your mind hasn't gotten the message yet. You're aware of the ceiling, the faint pressure of the mattress, the way the dark isn't perfectly dark, just reduced. And somewhere in that gap between tired and gone, a thought shows up that you didn't invite. It doesn't announce itself. It just sits there. If the universe is expanding, well, what is it expanding into? And here's the thing about that question. It doesn't feel complicated when it first arrives. It feels obvious. It feels like the kind of thing that should have a quick, clean answer, the sort of fact you half remember from a documentary, or a book you skimmed, or a classroom you were only partially present in. It feels answerable, and that's what makes it strange, because the longer you hold it, the more it starts to behave like something else entirely, not a question with a hidden answer, a question with a hidden problem in the question itself. I read about this once, or maybe I heard it, I can't remember where. Someone asked this at a dinner table, mid-meal, fork still in hand, and the table went quiet. Not because no one was smart enough to answer, because within about 3 seconds, everyone at that table quietly realized they didn't know what kind of question it was. That's the specific quality of it. The quiet it produces isn't ignorance, it's something more like vertigo. Most questions about space go quiet because they're big. The distances involved, the timescales, the numbers, they're just too large to sit with comfortably. You ask how far away a particular galaxy is, and the answer is technically an answer, but it doesn't land anywhere in your body. It just floats there, dimensionless. That's a different quiet. That's awe pushing language out of the room. This question does something else. This question goes quiet because it catches you smuggling in an assumption. And the assumption is so basic, so baked into the way you understand reality, that you didn't even know you were carrying it. The assumption is outside. The assumption is that if something is expanding, there must be something it's expanding into, a container, a background, some pre-existing space that was already there, waiting, into which the universe is slowly pressing. It's not an unreasonable assumption. Every expansion you have ever witnessed in your life has worked that way. Bread rising in a tin, smoke spreading across a room, a city growing into the land around its edges. In every case, a thing and then the space around the thing, and growth moving from the first into the second. The universe, as far as anyone can tell, does not have that. There is no second thing. There is no surrounding space. Or, and this is where it gets uncomfortable, the universe might be infinite, in which case it was never bounded to begin with, and expansion isn't growth toward an edge. It's more like every point moving away from every other point simultaneously, with nothing on the outside, because outside it doesn't apply. Neither of those is easy to picture. That's not a personal failure. They're genuinely not picturable. I want to take a breath here and say something about this channel, about the sleepy physicist, because this is the kind of question it was made for. Not the kind with tidy answers, the kind that reveals something about the shape of how we think. This is a self-funded project. No team behind it in the traditional sense, well, a team of 3 now, which still feels improbable. If something here pulls you towards stillness, or curiosity, or just a more interesting kind of tired, consider supporting the work on Patreon. It keeps this going, and the people who do, thank you genuinely. Alison, who's been here the longest, and Matthew M., and Brian Winter, and everyone else holding this space open. It matters more than I know how to say efficiently. Now, back to the dinner table, back to the fork. The reason the room went quiet, the specific reason, is that the question contains a flaw that nobody initially spots. And the flaw isn't in the physics, the flaw is in the word into. That single preposition is doing enormous, mostly invisible work. It presupposes a container. It presupposes that expansion is a kind of travel from here towards there, arriving somewhere that wasn't previously occupied. Take the word out, ask just the universe is expanding, no destination implied, just expanding. That's actually closer to what the physics says, but try telling your brain that. Try removing the implied container and sitting with what's left. What's left is deeply, stubbornly strange. The universe isn't a thing inside another thing. It isn't a bubble in a larger medium. It isn't a gas spreading through a room because there is no room. The expansion is the universe expanding, not the contents of the universe pushing outward, the universe itself, the space, the whole business. This is where most explanations reach for an analogy, and there are good ones, there are useful ones. But we're not going there yet. Ooh. Not tonight. Not this chapter. What this chapter wants to do, the only thing it wants to do, is let you feel the full weight of the question before any of the answers arrive. Because the answers are genuinely interesting. The physics here is strange in a way that earns that word. But if you get to the answers before you've really felt what's being asked, they just pass through you. They become another fact, another number or concept shelved and half forgotten. The question is, what is the universe expanding into? And before the answer can mean anything, you need to spend a moment with the version of yourself who doesn't know. Who's lying there, weight in the mattress, ceiling in the dark, and just holding it. The question that doesn't behave like other question, the question that feels answerable right up until the moment you actually try. That moment of trying, that slight interior lurch when the ordinary logic reaches for something solid and finds nothing there, that's where we're starting. The room didn't go quiet because the question was too big. It went quiet because the question was the right size, exactly the size of an assumption no one knew they were making. That's worth something. We'll find out what soon enough. Edwin Hubble did not discover that the universe was expanding. That's not quite right, or rather, it's not the whole shape of it. He didn't walk up to a telescope one night, peer through the eyepiece, and come back down the ladder saying it's all moving outward. It didn't happen like a revelation. It happened the way most things in observational astronomy happen, slowly across years, through a accumulation of numbers that kept refusing to behave. What Hubble did, what he actually did specifically, was measure. Distances, mostly. He was extraordinarily good at it, and extraordinarily committed to it. And if you read the papers he published in the late 1920s, they have this quality of careful, almost deliberate restraint, methodical to the point of being almost bloodless. The man did not editorialize. He reported, and what he reported in 1929 was a relationship between two numbers that turned out to be one of the stranger things anyone had ever written down. To understand what he found, you have to go back a little further, not far, a decade or so, to a problem that was bothering people who spent their careers looking at what were then called spiral nebulae. Nebulae. Clouds. The word itself carries a kind of softness, these small and faintly luminous patches in the sky, visible through even modest telescopes that had been catalogued and argued over for more than a century. The argument was simple and seemingly unanswerable. Were they inside our galaxy, or outside it? Were they nearby clouds of gas, relatively local, minor players in a Milky Way of fixed and knowable size? Or were they something else, entire systems, each containing billions of stars, each separated from us by distances so large that the word large stops doing useful work? The debate had a name, the Great Debate. which tells you something about how seriously people took it, and also about the era, a time when astronomy still had the vocabulary of argument rather than the vocabulary of data. Hubble ended it. Not dramatically, he ended it the way he ended most things, with a measurement. The trick was finding a reliable distance marker, something you could see in those blurred, uncertain patches, something with a known brightness, so that by comparing how bright it looked to how bright it actually was, you could calculate how far the light had travelled to reach you. The tool he used was a class of stars called Cepheid variables, stars that pulse, that brighten and dim on a precise clockwork schedule, and here's the part that matters, whose period of pulsation is directly tied to their intrinsic luminosity. The longer the pulse, the brighter the star. Always. It's a stubborn, reliable relationship first mapped by Henrietta Swan Leavitt more than a decade before Hubble used it, doing painstaking work that didn't receive, well, that's a different story and a longer one. The point is, Hubble found Cepheids in the Andromeda Nebula, measured their pulse periods, worked backwards to their true brightness, compared that to how they appeared through the telescope, and got a distance that put Andromeda so far outside the Milky Way that the question of whether it was inside our galaxy became almost funny in retrospect. Not a cloud of nearby gas, an entire galaxy, hundreds of billions of stars, nearly 1 million light-years away, though the actual figure, refined later, turned out to be closer to 2.5 million. The universe, in the span of one set of measurements, became enormously, almost offensively larger. But that's not the part I keep returning to. The part I keep returning to is what happened when Hubble combined his distance measurements with something that other astronomers had already been accumulating: redshift data. Spectra of those same galaxies, the light from them stretched, and light gets stretched, shifted toward the red end of the spectrum when the source of the light is moving away from you. The faster it moves, the more the light stretches. It's the same principle as the pitch of a train horn dropping as the train recedes, except it works on light instead of sound, and the scale involved is different. Vesto Slipher had already measured the redshifts of dozens of galaxies before Hubble entered the picture, and most of them were moving away. Not all. Andromeda famously is heading toward us, which creates its own set of questions for another night, but most. Slipher had the velocities, Hubble had the distances. When he put them together, what he found was this: the farther away a galaxy was, the faster it was receding. Not randomly faster, proportionally faster. A galaxy twice as far moved away roughly twice as fast. 3 times the distance, roughly 3 times the speed, a straight line on a graph. Clean, almost irritatingly clean, given the messiness of the measurements involved. That relationship, distance proportional to recession velocity, is what became Hubble's law, and it's taught usually as the discovery of the expanding universe. Which is where I want to be careful for a moment, because Hubble himself was careful. His 1929 paper uses the phrase apparent velocities, not velocities, apparent velocities. He was not certain, and he wrote it as not certain, that the redshift actually meant the galaxies were moving in the way a train moves, through space away from a fixed point. He saw a pattern. He reported a pattern. What the pattern meant, whether it was motion or something stranger, something involving the fabric of space itself, doing something unexpected to Bohr, that he left open. Or at least he left it more open than the textbooks that came after him. Other people were less restrained. Georges Lemaitre, a Belgian priest of all the pairings of vocations, had already derived from Einstein's equations the theoretical prediction that the universe should be expanding. He published it in 1927, in French, in a journal that didn't circulate widely. He was largely ignored until Hubble's data gave his math something to hold on to. Einstein himself had spent years inserting a fudge factor into his equations, what he called the cosmological constant, specifically to prevent his own theory from predicting an expanding or contracting universe. Because he assumed, as most people assumed, that the universe was static, eternal, not going anywhere. When the data came in, he reportedly called the cosmological constant his greatest blunder, though whether he actually used those words is, honestly, that's disputed. History is like that. What you're left with, standing back from all of it, is something odd and persistent. Not one person, not one night, not one clean moment of discovery. A measurement here, a theoretical framework there, a set of data someone else collected that turned out to be essential, a paper published in the wrong language in the wrong journal that sat unread for years. The universe announced itself as expanding the way most true things announce themselves. Gradually, through a slow accumulation of evidence that nobody fully understood, till it was impossible to read any other way. And even then, even after all of it, the question of what the expansion actually is, what it means for space itself, what it implies about edges and outsides and the geometry of everything, that question wasn't answered by Hubble's graph. That question was, if anything, made more stubborn. There's a particular texture to working at altitude, in a dome, at night. The cold comes through the metal. The instrument has a smell, machine oil mostly, and something electrical that's hard to name. The dome motor hums when the telescope tracks. This low vibration you feel more in your chest than here. I think about that sometimes when I think about Hubble. Not the intellectual achievement, the physical fact of it. Years of nights, years of cold, years of writing down numbers and going home and coming back and writing down more numbers. And the numbers in the end said, everything is leaving. Not poetically, not as metaphor, as measurement. Everything and every galaxy beyond the small gravitationally bound neighbourhood of our own local group is getting farther from everything else. The distances are growing, not because the galaxies are flying through space like debris from a central explosion, but, and this is the part we'll need to spend real time with, because the space between them is doing something that doesn't have an obvious word for it, something that Hubble's graph pointed toward but couldn't explain. That's what's waiting, not in the data. In the question the data kept quietly raising, what kind of thing is space exactly that it can do this? You probably have a picture. Most people do. It's not their fault. It's an almost inevitable image, the one that forms when someone first says the universe began with a big bang and has been expanding ever since. The picture is a point, then a burst, then matter flying outward in all directions, spreading into the darkness the way shrapnel spreads, the way fireworks spread, the way anything explodes, from a centre toward an outside through a space that was already there and waiting. It's a sticky image. That's the word for it. Not wrong in a simple, correctable way. Sticky. The kind of wrong that keeps reforming every time you think you've let go of it. I had it for years. Not as a belief exactly, more as background assumption, the visual that loaded automatically whenever the topic came up. The universe, a sphere of stuff, expanding outwards, with empty space on the other side of its edge, growing into the dark, pressing against nothing. And the thing is, for a long time it seemed to work. It seemed to account for things, galaxies moving away. Sure, they got flung outward. Everything receding? Yes, obvious the blast is still propagating. The farther something is, the faster it's moving away from us. Well, naturally, The things flung hardest travelled farthest fastest. It hangs together, this picture. That's the problem. But here are the things it can't account for. First, if the universe exploded from a single point, there should be a centre, some location in space that used to be the epicenter, the original site of the explosion, around which everything else is now arranged in a shell, like the skin of a balloon, blown outward and from a single breath. We should be able to look in one direction and see more galaxies, look in the opposite direction and see fewer. We should be able to triangulate, to locate at least approximately where the middle is. We can't. There is no such location. Every galaxy we observe recedes from us, not just the ones in front of us or to our left or concentrated in some quadrant of the sky. All of them, in every direction uniformly, the universe looks from any vantage point as if it is expanding away from exactly where you're standing, which either means we happen to occupy the precise centre of the explosion, which is staggeringly unlikely and also not supported by anything, or the explosion model is wrong. It's wrong. Second thing, and this one is subtler but it matters more, in an explosion, at any scale, the material is moving through space. The shrapnel travels, it departs from one location and arrives at another. The space it moves through is pre-existing. It was there before the explosion, it's there during, it'll be there after. Space is the stage, the explosion is the event happening on it. What cosmologists mean when they say the universe is expanding is something structurally different from this. They mean that the space itself is growing, not that things are moving through space, that the space between things is increasing. The galaxies aren't travelling anywhere. They're not departing from a central location and arriving somewhere else. They're mostly just sitting there, more or less. And the distance between them is getting larger because the medium they're embedded in is stretching. No, actually, let me be more careful. Stretching implies something that was tighter before and is looser now, like fabric, and that image has its own problems. What's actually happening is better described as space has more of itself than it did before. There is more space, not that it's stretched, that there is genuinely more of it. The separation between two galaxies grows not because either of them moved, but because the distance or the quantity of space between them has increased. That's not a thing that happens in explosions. That's a different category of event entirely. So why does the explosion image persist? Partly because it's the only large-scale expansion most of us have ever watched. A firework at a distance, the specific visual of it, silent if you're far enough away, just light spreading against dark sky. That image is available. It's stored. When something says expanding universe, the brain reaches for what it has. And what it has is the firework, the burst, the outward propagation from a point. And partly, I think, because the explosion image has a before, it is a cause that makes intuitive sense. Something built up pressure and released it, which satisfies a very deep cognitive itch. The need for things to begin for a reason, with a mechanism, with a narrative of tension and release. The actual picture doesn't quite give you that. Or it gives you something much stranger in its place, something that doesn't slot into the tension-release narrative at all. It gives you space itself doing something, space having a dynamic, space being in some sense a thing that behaves, which is, and I'm aware this is not a satisfying handoff, the part that requires its own time. What this chapter is really about is the moment of letting go, not of the Big Bang. That happened in some form. The evidence for it is layered and convergent and not seriously contested, but of the specific picture that came packaged with the name. The firework, the blast, the outward spray of matter into a pre-existing void. that picture has to go. Not because it's embarrassing to have held it, but because it's actively in the way. It's occupying the mental space where the real thing needs to sit, and the real thing is stranger, and in some ways quieter, and in some ways harder to hold. But it's also the thing that actually leads somewhere. The explosion image is a dead end. Follow it far enough and you hit questions it can't answer. Where is the center? What is space expanding and why does everywhere look like the middle? The real picture, or the closest thing to a picture that the physics allows, doesn't answer all of those questions either, but it answers them differently. It changes their shape. It turns some of them from unanswerable problems into questions that were slightly malformed to begin with, like the question of what the universe is expanding into, which, if the explosion model were right, would be a reasonable thing to ask. If matter is flying through pre-existing space, then fine. What is it flying into? What lies beyond the edge? But if space itself is what's expanding, if there's no edge because there's no fixed background it's pressing against, then the question shifts. It doesn't disappear, but it shifts. There's a photograph, not a real one, a thought experiment, of a sheet of rubber being stretched from all edges simultaneously. You mark 2 points on it. Pull. The points move apart. Now ask, which point moved? The answer is neither, really. Both moved relative to the other. The sheet grew between them. There's no trajectory, no direction of travel, just more sheet. That's closer. That's not the whole picture either, and we'll find out why soon enough. But it's closer than the firework. It's a photograph taken of the right thing, even if it's still a little blurred. The explosion was a photograph of the wrong thing, and now that it's been set down, the sticky, persistent, almost satisfying wrong picture, there's room for what actually needs to come in, which is the question of what space is, not what's in it, what it is. Start with the bread, not because it's the best way in, there might not be a best way in, but because it's the most generous way in. And generous counts for something when what you're trying to do is get a human mind to sit comfortably with an idea it was never built to hold. So, bread. Specifically raisin bread, rising in a warm kitchen. The dough is pale and soft and slightly tacky if you press your thumb into it, and it fills back in slowly, the indent closing over itself like it was never there. The raisins are distributed through it, unevenly the way raisins always are, clustered in some places, sparse in others, and the whole thing is growing. Now watch what happens to the raisins. Every raisin moves away from every other raisin. Not because any raisin has a direction, not because they're propelling themselves outward, not because there's some force pushing them toward the edges of the tin. The raisins aren't doing anything. The dough between them is expanding, but the stuff between the raisins, the bread part, the dough, or whatever you want to call it. And that expansion carries the raisins along as passengers. From any raisin's perspective, every other raisin is moving away. The nearby ones slowly, the distant ones faster, because there's more bread between them. And more bread means more expansion, means more separation per unit of time. A raisin 2 inches away recedes at a certain rate. A raisin 4 inches away recedes at roughly twice that rate. The relationship is proportional. The relationship is, in fact, exactly the proportional relationship that Hubble measured between galaxies. This is why people like this analogy. This is why it appears in almost every popular explanation of cosmological expansion. It actually works. It captures something real. The mechanics of it, passive recession, proportional velocity, no center, no edge of the bread visible from inside the loaf, these are genuine correspondences, not decorative ones. The warmth of that kitchen, the specific homey quality of something rising in an oven. I wonder sometimes whether Hubble, who was famously not given to whimsy, would have... No, that's a digression. Back to the bread. The analogy is generous. I mean that with some affection and some suspicion. A generous analogy is one that gives you more understanding than it technically has the right to. It hands you the feeling of comprehension before the full structure of comprehension is in place well. And the raisin bread does this beautifully. It makes passive recession feel intuitive. It makes proportional velocity feel obvious. It makes the expansion of space feel like something you can almost touch. But here is where the generosity starts becoming a kind of quiet dishonesty. The bread has a centre, not a philosophical centre. A literal, geometric centre, a point equidistant from all its edges, around which the dough is symmetrically distributed, from which, if you were a raisin, you could in principle measure your distance to the crust. If you baked this loaf and cut it open, you could find that centre. You could stand a raisin there and say, this one is in the middle. The universe does not have this. There is no location in the universe that is the centre of expansion. This has been tested repeatedly through the distribution of galaxies and the uniformity of the cosmic microwave background. The faint thermal glow left over from the early universe spread across the sky with a smoothness that indicates no preferred direction, no focal point, no axis around which the rest is arranged. Every point in the universe looks, from that point, like the centre of expansion. Because every point is receding from every other point. Because the expansion has no source location. In the bread, a raisin at the centre of the loaf would see nearby raisins moving away more slowly than distant ones. Fine, that's real. But it would also, if it could measure carefully enough, detect the asymmetry. The crust is out there. The edge exists. The raisins near the crust have less bread on one side than the other. The geometry is not the same at every point. That asymmetry doesn't exist in the universe. Or, more carefully, we have found no evidence of it in any direction at any scale we can currently probe. So the bread lies. Not about the mechanism of recession, about the geometry of the thing doing the receding. There's also the question of what's outside the bread. This is where the analogy collapses most completely, and it does so quietly, which is the dangerous kind of collapse. The bread exists inside a kitchen. The kitchen exists inside a house. The house exists inside a world that contains all the space the bread is decidedly not occupying. The bread is a finite object inside a larger medium. Its expansion is genuinely an expansion into something. The something is the air in the tin, then the space around the tin. This is exactly the picture we spent the last chapter dismantling. The universe object expanding into a surrounding void. The bread resmuggles it. You're sitting with this warm rising analogy, feeling like you understand, and the whole time the analogy is quietly handing you back the assumption you were supposed to have put down. That's what I mean by generous. It gives you the right mechanism and the wrong container. It shows you how the raisins move and then almost accidentally implies that the whole moving system is inside something else. It isn't. Or we have no reason to think it is. And we have good reasons to think the question might not even be the right shape. Here is what the analogy would need to do to be honest. The bread would need to have no centre. The bread would need to have no edge. The bread would need to be the only thing, no tin, no kitchen, no exterior air, no outside in any direction. The bread would need to be in some sense infinite, or alternatively, it would need to curve back on itself so that a raisin travelling in any direction would eventually, after an unimaginable distance, end up back where it started, but without ever encountering a wall, a crust, a surface, an edge. What you'd be describing then isn't really bread anymore. It's something that uses bread as a starting point and then asks you to let go of every bread-like property except one, the expanding medium carrying passive objects apart. That's the kernel, the one honest thing the analogy contains. Expansion as a property of the medium, not the objects. Distance increasing because the medium has more of itself, not because anything travelled. Everything else, the centre, the crust, the kitchen, the tin, set it down. None of it comes with us. There's a specific moment in handling raw dough, pressing your thumb in and watching the indent fill back in, where you can feel that the dough is not passive. It has a faint tension, a resistance. It pushes back against the shape you tried to make. The bread wants, in some minimal structural sense, to be itself. Space doesn't do that. Space doesn't resist. Space doesn't push back. Space doesn't have a preferred shape it returns to when you disturb it. Space. And this is what the bread can't capture, what no kitchen analogy can capture, is doing something far stranger than rising. It isn't a medium filling a container. It isn't a substance with an outside. It's a thing whose expansion has no destination, no edge case, no equivalent of the moment the bread hits the sides of the tin and stops. The bread stops. The universe, as far as anyone can tell, doesn't. And if space is the thing expanding, and not the contents of space, not the matter, but space itself, then the question that has been sitting quietly at the back of all this becomes unavoidable. What kind of thing is space that it can do this? What kind of thing has been expanding this whole time? For most of human history, space was polite. It didn't ask anything of you. It didn't push back. It sat there, perfectly inert, perfectly flat, the ultimate background against which everything else performed. Planets, stars, comets, whatever else needed somewhere to be. It was the stage. And the stage, in this conception, had no opinions. It didn't warp when something heavy stood on it. It didn't remember where things had been. It didn't participate. It held the geometry fixed and let matter get on with whatever matter was going to do. This was Newton's space. And it's worth saying clearly that Newton's space was not a naive idea. It was a useful idea. An enormously, almost embarrassingly useful idea. One that correctly predicted the motion of planets, the trajectory of cannonballs, the behaviour of tides, the return of comets, the shape of orbits across the solar system, for more than 200 years, with no meaningful exception and no serious rival. When people say Newton was wrong about space, there's a quality of ingratitude in it. Or there should be, because the man built a model that worked better than anything before it and better than most things after it, for nearly every practical purpose anyone could name. And yet, it was wrong about what space actually is. The irritant, as it often is in physics, was a question that seemed almost philosophical, almost not worth asking. The question was, Newton's space is absolute, but absolute relative to what? Ernst Mach asked this, or something very like it, in the 19th century, and he asked it with a persistence that bothered people precisely because it didn't have an easy answer. If space is a fixed background, a container that doesn't move or respond or change, what is it fixed relative to? You can say the Earth moves through space, but through space defined how? Anchored to what? Space that is absolute has to be absolute with respect to something, and the moment you reach for that something, you find there's nothing there to grab. Newton's answer, essentially, was that absolute space was just a fundamental feature of reality, irreducible, not anchored to anything else because it didn't need to be, not relative because it was the thing that other things were relative to, which is either a profound insight into the structure of the universe or a definition that hides a gap by calling the gap foundational. And the honest answer is that for 2 centuries nobody could tell which. Einstein could. Or rather, Einstein found a different way to ask the question, which turned out to be more productive than answering the old one directly. What if space wasn't a passive backdrop? What if it was a thing? An actual thing with properties, with behavior capable of being affected by what it contained, and capable of affecting what it contained in return? What if the geometry of space, the distances, the angles, the paths that objects follow, wasn't fixed by some abstract, absolute framework, but was instead determined locally, continuously, by the distribution of mass and energy in that region? That's the condensed version, and condensed versions of general relativity always feel slightly dishonest because the real structure is mathematical, and the mathematics does work that words genuinely cannot. But the core of it is this: mass curves space. Or more precisely, mass and energy curve space-time, the 4-dimensional fabric that general relativity works with, and the curvature of that fabric is what we experience as gravity. What feels like a force pulling you toward the Earth is actually the Earth's mass having curved the space-time around it, and you are following the straightest possible path through that curved geometry. Which means gravity isn't a force exactly, it's geometry. It's the shape of the medium, the rubber sheet. This is where people usually reach for the image of a heavy ball on a stretched rubber sheet, deforming it, creating a well that smaller objects roll toward, and it's a useful image as far as it goes, which isn't quite far enough. The image is 2-dimensional. It works visually in 2 dimensions because we can see the curvature. The actual curvature that general relativity describes is in 4 dimensions, including time, and human visual intuition can't hold that. What you can do is press your palm flat against something taut, a drumhead, a stretched piece of cloth, and feel it give under your weight. Not dramatically, just slightly. Feel the surface respond to the fact of you. That response, that's the relationship being described. Not a metaphor for it. Almost the actual thing, scaled down, stripped of the temporal dimension, lacking 3 spatial ones. Space responds to mass. It curves, it bends, it participates in the behavior of the objects inside it rather than sitting neutrally behind them. And the way space sort of tells things how to move and things sort of tell space how to curve. It's a 2-way. It's genuinely a 2-way thing, which is what makes it strange, and what makes every simple analogy for it slightly insufficient. The stage is not neutral, the stage is an actor. Now, what this means for expansion. If space is a thing, a dynamic thing, a thing that responds and curves and participates, then the idea that space itself can expand becomes not simple exactly, but at least coherent. Not a contradiction, not a category error. A thing that has geometry can have changing geometry though. A thing that responds can change. A thing with properties can have the property of expansion. In Newton's model, space expanding would be meaningless. The container can't grow because there's no mechanism by which a featureless, absolute, non-responding background could change size. Size relative to what? The question dissolves before it forms. In Einstein's model, the question becomes, what does the geometry of space-time do over cosmological scales when you account for all the mass and energy distributed across the universe? And when you write down the equations, the full equations are the ones Einstein was famously reluctant to let predict what they turned out to predict, the answer is that the geometry is not static. It doesn't sit still. The equations want it to either expand or contract. A static universe in general relativity is not the natural state. It requires a specific intervention, a fudge, a constant inserted by hand to prevent the geometry from doing what the geometry wants to do, and the geometry wants to move, and here is where something changes, not in the physics, but in the quality of the question we started with. If space is a container, then asking what it expands into is perfectly reasonable. Containers expand into the space around them. That's what containers do. But if space is not a container, if space is a dynamic geometric thing, a participant, a medium with no outside, because outside requires a reference frame that general relativity doesn't provide at cosmological scales, then the question changes shape. It doesn't go away, but it stops being a question about containers. It starts being a question about geometry, about what it means for a thing to have more of itself without having a larger thing to be inside of, which is a different kind of difficult. Not a frustrating difficult, a quiet one, the kind that asks you to sit with something that doesn't map onto any object you've ever held, any room you've ever walked through, any surface you've ever pressed your hand against and felt pushed back. Space is opinionated, in a way Newton's space wasn't. It curves, it expands, it revolves. It has, in some sense, a history. It has been different sizes, it has had different geometries, and what it is now is not what it will be. The thing with a history is not a backdrop. A backdrop doesn't change, what changes is real. There is still the question of what real means here. What it means to say space is something rather than simply containing something, whether the fabric is a useful shorthand or a genuine description, whether calling it a thing is philosophically rigorous or just the best language available for a structure that language wasn't designed to carry. I lean toward it's the best available, which is not the same as wrong, it's just honest about its limits. Space is not nothing. The evidence for that is overwhelming, from gravitational waves rippling through it to the bending of light around massive objects to the very expansion we're trying to understand. Whatever space is, it is not the polite, featureless backdrop of classical physics. It does things. It responds. It has been doing things since very early in the universe's history, things that set the conditions for everything that came after, including, at the very beginning, something so fast and so extreme that even the language of expansion starts to feel underpowered for it. That very early moment, the one that shaped the universe before anything we'd recognize as structure had formed, is sitting just ahead. Not to explain it, just to feel for a moment the scale of what space did when it was very young and not yet finished deciding what to be. Start with a number, 10 to the power of 26. That's the factor by which the universe expanded during inflation. Not the size it reached. The factor, the multiplier. Whatever size the universe was at the start of that period, it became 10 to the power of 26 times larger, which is 100 million billion times larger, which is a sentence that technically contains information and practically contains none, because the human number sense doesn't extend anywhere near that far, and pretending otherwise is a kind of performance. So don't perform it. Just hold the number at arm's length and notice that it doesn't fit. The time frame was, it's not rapid exactly. Rapid is what water does going over a rock. Rapid is a hummingbird's wings. What happened here occupied a window somewhere between 10 to the power of minus 35 and 10 to the power of minus 32 seconds after whatever the beginning was. 300ths of a trillionth of a trillionth of a trillionth of a second. A duration so small it exists below any physical process we can currently probe, below any instrument, below any unit of time that was coined for a reason other than to name things at that scale. In that window, space expanded by a factor that doesn't fit in a human head. Alan Guth wrote this down in 1980, on paper, from equations. with no direct observational evidence that it had happened, only the theoretical pressure of several problems that the standard Big Bang model couldn't solve. The flatness of the universe, the uniformity of the cosmic microwave background, the absence of certain exotic particles that should have been abundant if the early universe had cooled slowly. The math said something must have happened very fast, very early. Something must have smoothed everything out. And the smoothing had to have been this extreme, or the numbers didn't reconcile. He published it. People read it. Some were skeptical. Most eventually weren't. What inflation did to the universe is easier to describe than what it was. It's smoothed. That's the operative word, and it's worth sitting with how much violence that word is doing while sounding calm. The universe prior to inflation was, we think, we infer, we cannot directly observe, irregular. Lumpy at the quantum scale, with density fluctuations, with regions of slightly different energy, with the kind of small-scale chaos that quantum mechanics produces as a matter of course. Inflation took those fluctuations and stretched them so far that the irregularities which had existed at subatomic scales became the largest structures in the observable universe. The seeds of galaxy clusters, of the cosmic web, of everything you'd see if you could zoom out far enough to see everything at once. And everything else, every larger scale irregularity, every wrinkle in the geometry bigger than those quantum fluctuations, was erased, stretched to scales so vast they became undetectable. The universe that came out of inflation was, on the scales we can measure, almost perfectly flat, almost perfectly uniform, almost perfectly smooth in every direction. The almost is doing real work in those sentences. The tiny residual unevenness, the quantum fluctuations that inflation magnified rather than erased, those became galaxies. Without them, there would be nothing. A perfectly smooth universe after inflation would have stayed smooth. Uniform gas, expanding, never clumping, never forming stars or planets or anything else. The entire structure of the universe, everything that has any shape or density or gravitational pull, traces back to quantum noise that inflation happened to stretch rather than obliterate. But here's what this chapter is actually about. Inflation is also why we can't see the edge. Not because the edge is hidden behind something, not because the light from it hasn't reached us yet, though that's also true, separately, but because inflation almost certainly pushed whatever boundary the universe might have to scales so far beyond our observational horizon that no instrument we could build, no baseline we could use, no signal we could wait for would ever let us see it. If the universe is finite, if it has a topology, a shape, a size, inflation made that size at minimum tens of orders of magnitude larger than the observable universe. Maybe far more. The math doesn't give an upper bound. So when we ask where the edge is, and it's a reasonable question, the kind of question that deserves a real answer rather than a philosophical deflection, the honest answer is, we don't know if there is one. And if there is one, we have a near certainty that it is so far beyond what we can observe that the distinction between edge very far away and no edge is not currently and may never be empirically meaningful. That's not a satisfying answer, but it's the accurate one. There's a specific cognitive experience that happens when you work with these scales for long enough. Not wonder, exactly, or not only wonder. Something that feels more like static. The numbers get large enough that the mind stops producing a response to them. 10 to the power of 26 doesn't feel bigger than 10 to the power of 10. They are both just too large. Both just symbols on a page that gesture towards something the brain was never asked to handle. I notice this and don't know what to do with it. It seems important that the scales are this extreme. It seems like the extremity should mean something, should produce some proportionate response. And it just doesn't. The number sits there. indifferent. Which maybe is the right response. Indifference returned to indifference. Inflation doesn't know it smoothed anything. Inflation doesn't know it created the conditions for galaxies. Inflation doesn't know it pushed the edge of the universe, if there is one, beyond any horizon we'll ever see. It was a property of a field, the inflaton field, a theoretical construct whose exact nature is still debated, that caused space to expand at that rate for that duration and then stop. No intention, no direction, just a process that ran and then didn't. The universe that came out of it was flat and smooth and enormous and seeded with the exact right amount of unevenness to eventually become everything. That everything includes the question of where the edge is, which inflation, in a very practical sense, made unanswerable. Here is what we can say. The observable universe, the sphere of space from which light has had time to reach us since the beginning, extends roughly 46 billion light years in every direction. That number is larger than the age of the universe in light years, because space expanded while the light was travelling, carrying distant sources farther away than the light travel time alone would suggest. Beyond that 46 billion light-year boundary, there is almost certainly more universe, more space, more galaxies, or whatever the equivalent structure is at those distances. We can't see it, not because it's behind a wall, because the light from it hasn't reached us, and in many cases, because the expansion of space means it never will. Whether that more is finite or infinite, whether there is eventually an edge, a boundary, a place where the universe simply stops being, we don't know. We have measurements that constrain the shape of space within the observable universe. Those measurements say flat or very nearly flat, to within the precision of current instruments. A flat, simply connected space is infinite. But the measurements don't rule out a flat space with a complex topology, a space that is finite but so large that its finite nature is invisible at any scale we can currently probe. So, edge possibly exists. Edge possibly doesn't. Location of edge, if it exists, unknown and possibly unknowable. That's the whole answer. Small enough to fit in a paragraph. Strange enough to sit with for much longer. The question of the edge pulls at something, some deep preference for boundaries, for knowable limits, for the comfort of a thing that has a shape you can walk around. A universe with an edge is a universe you could, in principle, understand the totality of. A universe without an edge is something else, not frightening exactly, but demanding. It asks you to be comfortable with a kind of vastness that doesn't terminate, that offers no exterior view, no outside vantage point from which the whole thing could be seen. There is no outside vantage point. There is no view from nowhere. There is only inside looking. And the inside is, as far as the measurements go, as far as inflation's legacy extends, effectively without limit. Whether effectively without limit and actually without limit are the same thing is a question that sits just ahead in the geometry itself, in what it means for space to be shaped the way it appears to be shaped, and what shapes are even possible for something that has no outside. There are three basic options, not three theories competing for dominance, three geometric possibilities that general relativity permits for the large-scale structure of space. Three answers to the question of what shape the universe has, if shape is even the right word for something you're always inside of and can never step back from to look at directly. They don't feel the same. That's the thing that gets lost when they're listed as options in a textbook. 3 bullet points with equal margins and identical font sizes. They feel different. They imply different things. They ask different things of the person trying to hold them. The first one is the closed universe. Positive curvature. the geometry of a sphere extended to 3 spatial dimensions in a way that can't be visualized directly but can be approached from the side. On the surface of a sphere, if you travel far enough in a straight line, you come back. Not because you turned, because the geometry curves, because straight in that space is not the Euclidean straight you learned about in school. It's the straightest path available in a curved medium, and the medium curves back on itself. A closed universe would work the same way. Travel far enough in any direction without deviating, and then eventually, after an unimaginably long journey, longer than any ship or signal could accomplish in the age of the universe, you'd find yourself approaching the place you left from the other side. No wall encountered, no edge reached, just the geometry returning you. There's a romanticism to this that I want to name and then gently puncture. The idea of a universe that curves back on itself has this quality of completeness, of tidiness, everything connected, nothing truly lost, all paths eventually rejoining. It's a tidy universe. And I'm suspicious of tidiness in cosmology, because the universe has never, in any observational measurement, shown particular interest in being neat. A closed universe is also a finite universe. It has a total volume, a number in principle that you could assign to the amount of space there is. Whether that number is knowable is a different question. Whether it's finite is not. In a closed universe it is. The universe has a size, which is either reassuring or strange depending on what you are expecting. Current measurements don't support it, or not strongly. The curvature parameter measured from the cosmic microwave background sits so close to zero that a positively curved universe would have to be so large that its curvature is invisible at observable scales. Possible, not favoured. The second is the hyperbolic universe. Negative curvature, the geometry of a saddle or a Pringle, or any surface that curves away from itself in 2 directions simultaneously at every point. In a negatively curved space, parallel lines diverge. Triangles have angles that add up to less than 180 degrees. The geometry opens outward rather than closing inward. It doesn't return you, it keeps going, and as it goes it gets wider, more spread, more... There's a word for this I keep almost reaching and not quite finding. Ungovernable, maybe. The hyperbolic universe is ungovernable. What this means practically, a hyperbolic universe is infinite. It doesn't loop back. It doesn't have a total size. It expands forever. Both in the sense that the cosmological expansion continues indefinitely, and in the geometric sense that the space itself has no bound, no edge case, no place where the saddle stops curving and something else begins. Travel in a hyperbolic universe and you don't come back. You keep going. The space around you keeps opening. The angle between any 2 paths you might have taken keeps widening. There's something vertiginous about that. Something that doesn't resolve into comfort the way the closed universe does, or tries to. The hyperbolic universe doesn't offer a return. It offers more. Is more comforting? I don't know. Depends what you wanted. Also not strongly favoured by current measurements. The curvature parameter again sits near zero, too near to clearly indicate negative rather than flat. Though the error bars are small but not zero, and small but not zero leaves room. The third is the flat universe. Zero curvature. Euclidean geometry at large scales, the same geometry that works for rooms and roads and the distances between cities. Parallel lines stay parallel. Triangles have angles summing to exactly 180 degrees. There's no intrinsic curvature pulling paths together or pushing them apart. And flat is... Here's where the word causes problems, because flat sounds simple. Flat sounds like the easiest option. Flat sounds like the one that requires the least imagination. It isn't. Flat is the most unsettling of the 3, and I mean that as a description rather than a judgment. A flat, simply connected universe is infinite, Not almost infinite, not effectively infinite for practical purposes. Infinite, right now. No boundary in any direction at any distance. Space continuing without limit, containing, if the large-scale structure continues as it does within the observable region, roughly the same density of galaxies per volume, on and on, without termination. Try to hold that. Not the number, not the concept, but the actual spatial implication. An infinite flat space means there are, right now, infinitely many galaxies, infinitely many stars, infinitely many planets. The observable universe, that 46 billion light-year sphere we can see, is an infinitesimally small patch of a thing that has no size, because size implies a boundary, and there isn't one. That's what flat implies. Not a plane you could eventually cross, a plane that doesn't end, not in principle, not in practice, not ever. I grew up near enough to flatland to know what a large horizon feels like. The ground gives you nothing, no hill to orient by, no feature that lets you know you're getting closer to anything. Just distance, equal in every direction, and the sense that the world is not going to reward continued travel with arrival. It's a specific feeling, not frightening exactly, more like the landscape refusing to make promises. A flat universe is that feeling, extended without limit, in 3 dimensions, with no horizon, because there's nothing to be a horizon against. The measurements favour it. The Planck satellite's final data release puts the curvature parameter at 0.0007 plus or minus 0.0019. Consistent with 0, consistent with flat, to the most precise measurement currently possible. This is what the cosmic microwave background tells us about the geometry of space at the largest scales we can probe. It says flat, or so close to flat that the difference, if there is one, is invisible. Now, flat and infinite is one option, but there's a wrinkle, and it's a wrinkle that matters more than it might initially seem. Flat doesn't mean simply connected. A flat space can have a complex topology. It can be finite in volume while still being locally flat, the way a torus is locally flat. If you live on the surface of a donut, the local geometry at every point looks Euclidean, looks flat, but the global structure is finite and wraps back on itself. A sufficiently large flat torus would look from the inside identical to an infinite flat space, until you found the matching patterns, the repeated images, the places where the light had wrapped around and come back. We've looked for those patterns, in the CMB specifically, searching for pairs of circles with matching temperature profiles that would indicate we're looking at the same region of space from 2 different directions. We haven't found them. But as recent work has shown, the constraints on what topologies can be ruled out are significantly looser than people thought. Many shapes dismissed as impossible are back in consideration. So, flat probably, infinite possibly, but the possibly carries more uncertainty than it used to. 3 shapes, 3 emotional textures, 3 different answers to what it means to be inside a thing with no outside. The closed universe says, you could return given enough time to where you began. The hyperbolic universe says, you won't, and the going is all there is. The flat universe says, there is no meaningful difference between going and staying, because the going never ends, and the staying is always somewhere in the middle of something boundless. None of them is easy. None of them resolves into a picture you can hold comfortably. The best you can do is feel their different weights, the different quality of strangeness each one carries, and notice that the universe, whatever shape it has, is not the kind of thing that fits in the mental space you came with, which is fine. The mental space can adjust. It adjusts slowly usually, over nights like this one, in increments too small to notice. And the next step in that adjustment is the thing that might be the strangest of all, the possibility of a universe that is finite, bounded in total size, and yet has no wall, no surface, no place where the inside stops and the outside begins. Pick up something round, A ball, an ornament, anything with a curved surface and no corners. Run a finger along it. Keep going. Your finger travels, it covers distance, it moves through space relative to the object, and it never, not once, not at any point in the journey, reaches a place where the surface ends. There is no drop-off, no edge where the material stops and the air begins. The surface just continues curving, returning your finger eventually to the place it started without ever offering an exit. The surface of a sphere is finite. You could calculate its area. You could assign it a number. In that sense, it is bounded. It has a measurable size, a total extent, an amount of surface that is not infinite. And yet it has no boundary, no edge, no place where inside meets outside. Because on the surface itself, there is no inside or outside. There's just surface, continuous, uninterrupted. This distinction between finite and bounded on one hand and unbounded in the sense of having no edge on the other is the thing this chapter exists to sit with, because it's the thing the universe might be doing, and it's genuinely, stubbornly hard to hold. Here's what I mean by impolite. Infinity is hard, but it has a certain coherence. You can point at it. You can say, it goes on forever. There is no end. The space just continues without limit. That's difficult to picture, but it's not paradoxical. It doesn't violate any expectation except scale. A wall is also coherent. The universe has a total size. You travel far enough, and you hit something, or the space stops, or the geometry terminates. That's uncomfortable, but it's imaginable. The mind can reach for it. Finite without boundary refuses both. It says there is a total amount of space, a finite volume, a number, unknowably large possibly, but a number. And there is no wall, no edge, no place where the number becomes visible as a limit. You travel and you find more space, and then one day, after a journey no physical object could make in the current age of the universe, you find yourself back where you started, without ever having turned, without ever having bounced off anything, without any local signal that anything unusual happened. It refuses the comfort of infinite space and the comfort of a wall you could press your hand against, and offers instead something that is neither. That's what I mean by impolite. It doesn't meet you where your intuition lives. The geometry that permits this is called a closed manifold. Or, more precisely, the topology. And topology is a different thing from geometry, which is worth being careful about because the two are often conflated, and the conflation causes confusion. Geometry is local. It describes the curvature of space at each point, the angles of triangles, whether parallel lines converge or diverge. Topology is the global sort of connectedness, the way the whole thing is stitched together at the large scale. Two spaces can have identical local geometry and completely different topologies. A flat piece of paper has flat geometry. A torus, a donut shape, also has flat geometry on its surface locally. At every point on a torus, if you zoom in closely enough, the surface looks Euclidean. The angles work out the same as they do on a table, and yet the torus is a completely different global structure. It's finite. It wraps. If you're an ant on a torus and you walk in a straight line, you eventually return to your starting point without ever encountering an edge. This is the key move in the argument. Flat geometry, which is what our measurements currently support for the universe, does not require infinite space. A flat universe with a non-trivial topology could be finite, could be a three-dimensional version of a torus, or one of several other possible shapes, and would still look locally flat at every point inside it. You'd measure the angles of triangles and get 180 degrees. You'd see no intrinsic curvature, and if the topology's scale is large enough, larger than the observable universe, you'd see no sign of the wrapping either. Think about what it would mean to reach the edge if a finite universe had one. You're travelling, some impossible journey, faster than light for the sake of the thought experiment, out through the cosmic web, past the last galaxies, past whatever structure exists at the largest scales, toward the limit of the total space. What do you see when you get there? In a universe with a hard boundary, general relativity doesn't actually tell you what you'd find. The equations don't produce an edge as a natural solution. They produce geometries, curvatures, manifolds, and none of the standard solutions include a wall. A wall would require something outside the universe pressing against it, defining it, giving it a surface to be on one side of. And there's nothing outside, or rather, outside is a word that requires a larger space for the universe to be inside of, and we have no reason to think that exists, and significant mathematical reasons to be suspicious of the assumption. So if you travelled to where the edge should be, in a finite universe with no boundary, you wouldn't see an edge, you'd see more space. Because the topology would return you, the space would continue, not because it's infinite, but because it connects back to itself. The edge isn't absent because you haven't reached it. It's absent because the geometry doesn't include one. That's the thing the brain keeps reaching for and not finding. The wall. It keeps expecting a wall. There's a thought experiment sometimes used to approach this. A corridor. Imagine a corridor that is finite in length with no doors, no windows, no exits. You walk it. You reach what should be the end. And instead of a wall, you find yourself entering the corridor again from the other side, as if the two ends were connected. Not through a door. The space itself is connected. The end is the beginning. The geometry returns you. No, actually, that's not quite right either. The corridor analogy implies a specific direction of return, a specific axis along which the wrapping occurs. The topologies being proposed for the universe are more symmetric than that, and more complicated. A three-dimensional torus wraps in three independent directions simultaneously. Other proposed topologies, the Poincare dodecahedral space for instance, have more complex identification patterns, where faces of a dodecahedron are matched to opposite faces with specific rotational offsets, producing a finite space with a highly symmetric structure. What these all share is the property I keep circling. Finite volume, no boundary, locally indistinguishable from infinite space, unless you either make a journey of cosmological length or find the matching patterns in the CMB. We've looked for the patterns, they haven't shown up, but as the compact collaboration found recently, the constraints on possible topologies are significantly looser than the field had assumed. Many shapes thought to be ruled out require a second look. The search is genuinely open. Here is the thing that I find hardest about finite without boundary. Harder than infinite space, harder than a wall, harder than curvature or topology or any of the technical machinery. It's that the concept requires you to give up the question what's outside without giving you anything to replace it with. Infinity at least lets you say, there's more, always more, in every direction. That's a kind of answer to what's outside. The answer is more inside. A wall lets you say, outside is something else, something we can't access, but something, a place, a void, anything. Finite without boundary says, outside doesn't apply, not because we can't reach it, not because it's hidden, because the geometry doesn't include an outside. The universe is not a thing with an exterior. It's a thing whose every path eventually returns to itself, a closed structure in the topological sense, with a finite volume and no surface that could be on one side of anything. The question, what is the universe expanding into, assumes an outside, finite without boundary, along with infinite flatness. Along with every serious cosmological model currently on the table, all of them, in different ways, remove that assumption by answering the question. by showing that the question contains a structure that doesn't match the thing it's asking about. A finger tracing a sphere's surface, the travelling that never ends, the absence of a place to stop. That image, which started as a modest analogy for a surface, turns out to be doing more work than it first appeared. The sphere is two-dimensional. The universe is 3, maybe 4 if you count time as entangled with the spatial geometry in the way general relativity does. But the property being pointed at, the closure, the return, the refusal to offer an edge while still being measurably finite in its total extent, that property is the same. The finger doesn't find an edge because there isn't one. Not because the sphere is infinite, because the shape doesn't include that kind of ending. And if the universe is something like that, if it is, in its entirety, a structure that returns rather than terminates, then what it's expanding into is not a space outside itself. What it's expanding into is more of itself, which is either a satisfying answer or a way of showing that the question needed different words from the beginning. There is light travelling toward you right now that will never arrive, not because it was deflected, not because something absorbed it, because the space between you and its source is expanding faster than the light can cross it. It's moving away faster than the light can close the gap, if that makes sense, which geometrically it does, even if it sounds wrong at first. The light is moving, it is genuinely in motion at the speed of light, which is as fast as anything gets, and the distance it needs to cover is growing faster than it can cover it. So it travels faithfully in the right direction, and it falls behind anyway, and it will keep falling behind for the rest of time. It left its source before there were stars in the Milky Way, before the solar system existed, in some cases before the universe was 1 billion years old. It has been in transit for longer than almost anything you could name, crossing a universe that was smaller when it left, and has been expanding beneath it ever since, stretching the space it's moving through, lengthening the journey in real time while the journey is being made, and it will not arrive. Think about what it means to send a letter across a city where the streets are lengthening. You drop it in the post. The letter moves at whatever speed letters move. But the blocks between you and the recipient are getting longer, not because anyone is building new streets, but because the distance itself is increasing, every meter becoming more meters, the space between points quietly accumulating more of itself. If the lengthening is fast enough relative to the letter's speed, the letter makes progress and loses ground simultaneously, edging forward and falling further behind at once. From the letter's perspective, if letters had perspectives, it is moving. It is doing everything right. It just can't get there. The universe is that city. The photons are those letters, and the cosmic event horizon, the boundary beyond which light can never reach us, is the distance at which the expansion rate exactly cancels the progress of light. Anything closer than that horizon, the light gets through eventually, given enough time. Anything beyond it, the light is already losing ground, already falling behind, already committed to a journey that will not end in arrival. That boundary sits roughly 16 billion light-years away from us currently. Not the edge of the observable universe, that's a different number, 46 billion light-years, representing how far the light we can currently see has travelled since the beginning, accounting for the expansion that stretched those distances over time. The event horizon is closer, is the live boundary, the one that applies to light being emitted right now, today, at this moment. Sources beyond 16 billion light-years are already, as of now, unreachable. Their light is already losing. We will never receive anything new from them, not because they've stopped emitting, but because what they emit can no longer complete the journey. The observable universe, then, is a sphere roughly 46 billion light-years in radius. Everything we can see, everything we can measure, everything we know, the large-scale structure of all of it is inside that sphere. It is in any practical sense an enormous amount of space. Hundreds of billions of galaxies by current estimates. Structures spanning hundreds of millions of light years. More than enough to spend several careers studying. More than enough to spend a life looking up at. But it is not the universe. It is the part of the universe that has managed so far to get light to us. What lies beyond it is real, or we have every reason to think so, because there is no physical mechanism that would cause the universe to simply stop at the boundary of what we can observe. That boundary is not a wall, it's a horizon, the kind defined by time and the speed of light and the expansion rate, not by any property of the space itself. Beyond it, almost certainly, is more universe, more galaxies, more structure, more space, all of it existing and evolving and interacting with itself, utterly indifferent to whether we can see it. We cannot see it. Not with any telescope, not with any signal, not in principle, not ever, because the expansion of space has already sealed those regions off from any future causal contact with us. What was once in the very early universe, before expansion accelerated, potentially reachable, is now structurally, permanently beyond reach. Dark energy, whatever it is accelerating the expansion, and as the expansion accelerates, the event horizon contracts in moving terms, meaning that sources currently just inside our reach will eventually cross the boundary and go dark. The observable universe is slowly shrinking, not because space is contracting, it isn't, because the accelerating expansion is progressively moving more sources beyond the horizon of what can ever reach us. There is a specific quality to light from a source that no longer exists. A star dies. Let's say it collapses or explodes, or simply burns through its fuel and goes cold. The last light it emits leaves the surface and begins its journey. That light doesn't know the star is dead. It carries the frequency, the spectrum, the information of the fire that produced it, and it travels, genuinely carries that information for however many thousands or millions or billions of years the journey takes. When it arrives, if it arrives, it is still warm in the sense that it is still light, still energetic, still encoded with the story of a moment that is completely finished. You look up at a star and you're not seeing the star. You're seeing a message from a moment in the star's history, a moment that may be millions of years in the past, a moment that the star itself has entirely moved on from. In some cases, in many cases, the star no longer exists in anything like the form that produced the light you're seeing. You're receiving a letter from someone who has already left the address. Most of the time this fact sits quietly in the background. It's known, it's acknowledged, and then it's set aside because the light is there, and the star appears to be there, and the distinction between appearance and reality at that scale doesn't feel urgent. But for the light beyond the cosmic horizon, the distinction is all there is. That light will never be received. No one will ever look up and see it. It is travelling faithfully, through expanding space, carrying its information, encoding the moment of its emission. And the destination is not receding in the sense that a train platform recedes when you've missed the train. The destination is genuinely unreachable. The geometry of the universe as it currently behaves has made receipt impossible. The light doesn't know, it just goes. There's one exception worth naming, one direction in the sky where the rule doesn't apply. Andromeda is coming. The Andromeda galaxy, 2.5 million light-years away, the nearest large galaxy, a system roughly the size of the Milky Way with its own hundreds of billions of stars, is moving toward us. Its local motion, its peculiar velocity relative to the Hubble flow, happens to be directed our way. It will collide with the Milky Way in roughly 4.5 billion years, a collision that will take hundreds of millions of years to complete and will not destroy either galaxy, so much as intermingle them slowly, gravitationally, like two handfuls of sand poured together. Its light is blue shifted, coming this way, compressing the wavelength rather than stretching it, one of the very few nearby things not receding. I mention Andromeda because it's a useful reminder that the expansion is not total. It doesn't govern everything at every scale, and gravitationally bound systems are exempt from it in their local dynamics. The Milky Way and Andromeda are bound. The local group of galaxies is bound. At scales larger than that, the expansion dominates, and recession takes over, and the distances grow. But Andromeda comes for now. What I keep returning to, and I've thought about this more than is probably necessary, is the light in transit. The photons right now in the space between here and the unreachable regions, moving in the right direction at the right speed, doing exactly what photons are supposed to do. There is no failure in them, no flaw in their propagation. They are travelling correctly through a universe that has simply arranged itself such that travelling correctly is not enough. That is, I think, the most quietly devastating fact in cosmology. Not the scale of the universe, not the age of it, not the likelihood of other intelligences we will never contact, just this. Light that is doing everything right, carrying real information about real things that really existed, and will not deliver it, will travel forever, or until the heat death of the universe renders the distinction between travelling and not travelling meaningless without a rival. The universe is full of it. Faithful light going nowhere, it will ever be received. It does not feel like loss exactly. Loss requires something that was had. These photons were never going to arrive. The geometry was against them from the beginning. But it is adjacent to loss. It has that texture, the irreversibility of it. The fact that receipt is not delayed, but structurally, permanently impossible. The observable universe is not the universe. It is the part the universe has managed to show us so far, within the constraints of its own geometry and the speed of light and the time that has elapsed. What is beyond it is real. What is beyond the event horizon is real and for us, permanently invisible. And all of it, the observable part and the unreachable part both, is expanding, growing. The space between every unbound pair of objects increasing quietly, at every moment, at a rate that varies by distance and is governed by things we understand partially and name dark energy, without fully knowing what the name refers to. All of it is doing this with no outside to do it into. The light that left before we were here is still going. It does not need a destination to be real. It is out there, in the expanding dark, carrying the record of moments that are finished, moving through a universe that has no edge for it to eventually reach. It just travels, and it will keep travelling while the universe keeps expanding into distances that are not places so much as accumulated separations. Space that is more of itself than it was, more than it has ever been, more than the light will ever cross. What that more consists of, what kind of space it is, and whether it eventually returns or simply continues, is not a question the light can answer. It's a question for the geometry, for the shape of the whole thing, if the whole thing has a shape. The word briefly is doing almost dishonest work in this chapter's title. The duration of inflation, the period of exponential expansion in the very early universe, was somewhere between 10 to the power of minus 35 and 10 to the power of minus 32 seconds. 0.03 of a trillionth of a trillionth of a trillionth of a second. A number so small it exists entirely outside any scale human experience has ever needed to work with. Briefly in the context of a human life means a few seconds, maybe a minute. Briefly in geological time means thousands of years. Briefly here means a duration so compressed it has no analogy in anything that has ever happened at human scale or animal scale, or planetary scale or stellar scale. And in that duration, the universe expanded by a factor of at least 10 to the 26th power. Those are the two numbers. They sit there on the page, inert. They don't become an experience. You can read them, you can understand what they denote, you can do the arithmetic and confirm that yes, a factor of 10 to the power of 26 is approximately 100 million billion, and the duration is approximately nothing. And nothing happened in approximately nothing time and produced approximately everything, and the numbers still just sit there. They don't open up. They don't produce the sensation of scale they should, if sensation were proportional to fact. I've sat with these figures long enough to stop expecting them to land. They don't land, they just are. The mechanism was a field. A field. And field here means something specific in physics. Not a meadow, not a region, more like a property that space had or a condition it was in temporarily, called the inflaton field. This field had a characteristic that made it behave like a source of negative pressure, which in general relativity acts as a gravitational repulsion rather than attraction. Space under these conditions expanded exponentially. Not the contents of space accelerating outward. Space itself acquiring more of itself at every point simultaneously, at a rate that scales in a way ordinary expansion does not. The inflaton field was twitchy, unstable in a very specific fussy way. It couldn't maintain that state indefinitely, and the theory requires that it decay relatively quickly, dumping its energy into particles and radiation in a process called reheating, which produced the hot, dense state that the standard Big Bang model begins with. So inflation ended, the field decayed, the exponential expansion became the slower, decelerating expansion of a radiation-dominated universe, and then the matter-dominated universe, and eventually the dark energy-dominated universe we currently inhabit. What came before inflation? Whether before is even a meaningful word for the state prior to the inflaton field dominating, given that time itself is entangled with the space-time geometry that inflation was transforming, is not something the theory addresses cleanly. There's a prior, or something like a prior, but it's shadowed. The equations don't reach confidently into it, whether it was a quantum fluctuation, or a tunneling event from some earlier state, or something else that doesn't have a name yet. The honest answer is that we don't know, and the theories that attempt to describe it are speculative in a way that the inflationary model itself is not. Alan Guth, who first proposed this in 1980, was trying to solve three specific problems with the standard Big Bang model: the flatness problem, the horizon problem, the magnetic monopole problem, and found that a period of exponential expansion resolved all three simultaneously. There's something particular about that kind of theoretical moment. Not a prediction confirmed by observation, not yet, just a mathematical structure that, when written down, quietly erases three separate headaches at once. The specific texture of sitting with a problem that keeps failing to close and then finding that one assumption, changed, makes it close. I imagine that's what it felt like. Though I'm speculating. What inflation did to the universe is easier to inventory than what it was. Flatness. Whatever geometry the universe had prior to inflation, whatever curvature, whatever deviation from flat, was stretched to invisibility. When a sphere is expanded by a factor of 10 to the power of 26, the local surface at any point becomes indistinguishable from flat. The curvature that was there before is still there technically, but at scales so vast that no measurement within the resulting universe can detect it. This is why the universe appears flat, not because it started flat, because anything that wasn't flat got stretched until flat was the only description that applied at observable scales. Smoothness, the large-scale uniformity of the universe, the fact that the cosmic microwave background has the same temperature in every direction to 1 part in 100,000 traces to inflation having stretched any large-scale irregularities beyond the observable horizon. Structures that were bigger than the inflationary horizon at the time were erased from view. What remained was the small-scale quantum noise, the irreducible fluctuations that quantum mechanics produces regardless, and those got stretched to cosmological scales and became the seeds of everything. Scale-invariant fluctuations. The density perturbations inflation produced are distributed across scales in a specific way, roughly equal power at every scale, what physicists call a nearly scale-invariant spectrum. This was predicted before the SEMBI was measured with sufficient precision to check it. When the measurements came, from Kobe in 1992, from WMAP, from Planck, the spectrum matched, not approximately, with a kind of precision that makes theorists visibly relieved in their published papers. An enormous universe, the observable universe, at 46 billion light-years radius, is a small patch of the full post-inflationary space. How small depends on the details of the inflationary model, but the full universe is almost certainly at minimum tens of orders of magnitude larger than what we can observe. If the universe has a finite size, that size is so large that its finiteness is currently and possibly permanently undetectable. That last item is the one I keep returning to. Inflation didn't just make the universe large, it made the universe's own structure invisible to itself. If the universe has a topology, a global shape, a way of connecting back to itself, a finite volume, inflation stretched that topology to scales beyond our horizon. The matching patterns in the CMB that would reveal a non-trivial topology are absent not because the topology doesn't exist, but because inflation pushed the repeating scale beyond what any observation within this universe can reach. The universe, in a very specific sense, cannot see its own shape. Not because the shape is hidden behind something, because the process that produced the conditions for everything else also, incidentally, made the large-scale geometry inaccessible from the inside. We are inside a structure whose global properties were sealed off from observation before the first proton formed. That's not a tragedy. It's not framed as one in the literature. But it is. There is a word for this that I keep almost using and then not using because it sounds more dramatic than I mean it. It is a peculiar kind of closure. The universe producing its own opacity. The expansion that made everything possible also making everything's context invisible. Here is what remains after all the numbers. A universe that is flat, or very nearly so. Smooth at large scales, structured at small ones. Full of the residue of quantum fluctuations that became galaxies. Enormous beyond any figure that produces a response in the human body. Expanding still, at a rate governed now by dark energy rather than the inflaton field, slower than inflation by every measure but accelerating rather than decelerating. And somewhere in all of that, a specific moment that lasted less than nothing, less than any unit of time coined for a practical purpose, in which space did something so extreme that the word rapid fails on contact and the numbers that describe it sit on the page, refusing to become experience, and the universe that resulted is the only context in which any of this can be known. The exhale after it has been going on for 13.8 billion years. We are somewhere in the middle of that exhale, not at the beginning of it. The early universe was nothing like this. Not at the end. The end, if there is one, is so far ahead it might as well not be directional. Somewhere in the long, slow, dark, energy-driven expansion that followed the most violent beginning anything has ever had. The question of what the universe is expanding into has been sitting with us through all of this. And inflation, more than anything else in the story, is why the question is so hard to answer from the inside. The inside is all there is, and the inside was made unreadable to itself at its very beginning by the same event that made it. What's left then is the shape, the global structure, what the universe looks like not from any point within it but as a whole, if as a whole is something it's possible to be. That's what's coming. The question of topology, and what we've actually looked for, and what the looking found and didn't find and might still find. The oldest light in the universe is also, in a specific and useful sense, the only map we have of the whole thing. The cosmic microwave background, the CMB, is thermal radiation released approximately 380,000 years after the beginning, when the universe had cooled enough for electrons and protons to combine into hydrogen atoms, and the plasma that had been opaque to light became suddenly transparent, and the light that had been trapped inside that plasma was released all at once, in every direction, from every point in space simultaneously. That light has been travelling ever since. It has been stretched by the expansion of space from the wavelengths of visible light down to microwave frequencies, cooling from roughly 3,000 Kelvin to the 2.725 Kelvin it sits at now, and it arrives at our instruments from every direction in the sky with the uniformity that is, when you think about what produced it, almost unsettling. We have mapped it in extraordinary detail. The WAM-AP satellite spent 9 years on it, and the Planck satellite improved on WAM-AP's resolution significantly, producing a full sky map of temperature fluctuations at a precision that would have seemed implausible to cosmologists 30 years ago. Those fluctuations, tiny variations, 1 part in 100,000, carry information about the early universe, about its composition, about its geometry, about its age, and potentially about its topology. Here's what they were looking for. Essentially, the universe leaving fingerprints, specific patterns in the CMB that would only be there if space wraps back on itself in a particular way. If the universe has a non-trivial topology, if it is, say, a three-dimensional torus, or a Poincare dodecahedral space, or any of the other finite topologies that general relativity permits, then we should be able to see the same region of space from multiple directions. Light from a sufficiently distant source would reach us via more than one path, having travelled around the universe's topology in different directions and arrived from different angles. The signature of this would be pairs of circles on the CMB sky with matching temperature patterns, not similar patterns, identical, or near identical, within measurement uncertainty. Because both circles would be looking at the same ring of space from different vantage points. The universe, in effect, handing us the same receipt twice, stamped from 2 different directions. If you found those circles, you would know, not infer, not suggest, know, with the kind of directness that most cosmological conclusions don't enjoy. You would know the universe is topologically non-trivial. You would know something about the scale of the topology from the angular size of the circles, and you would have, in one result, answered the question that has been sitting behind every chapter of this in the most concrete way possible. Imagine what that would be like, in a control room somewhere, The moment the algorithm flags two circles with matching temperature profiles and someone goes very still, the search was carried out. Multiple teams, multiple methods, the Planck data, the DuMAP data, various systematic approaches to the problem. They looked for matched circles at every angular scale, every orientation, every possible pairing. They set up the search to detect topologies whose fundamental domain, the repeating unit, the basic cell of the topology, was smaller than the observable universe, because that's the regime where matching circles would actually appear in the CMB. They didn't find them. This is reported in the literature as a constraint, which is the correct word. Ruled out is a stronger claim than the data justify, and the field is careful about this distinction, or tries to be. What the non-detection means is, if the universe has a non-trivial topology, the fundamental domain is probably larger than the distance to the last scattering surface, the surface from which the CMB light was emitted. That puts the repeating scale, if there is one, at greater than roughly 26 billion light-years across, larger than anything the CMB can show us, larger than we can probe with current instruments. That was the state of the consensus for some years. Non-trivial topology, not found, possibly ruled out for scales within the observable universe, assumed by many to be either absent or so large as to make no observable difference. Here is where it gets more interesting and more honest about what science actually does. The Compact Collaboration, a group assembled specifically to work on cosmic topology, published results recently showing that the constraints established by prior searches were significantly weaker than the field had been treating them. The methodology used to rule out certain topologies assumed specific orientations for the matching circles, looked for them in specific ways, and concluded absence more broadly than the methodology justified. The actual minimum scale at which a non-trivial topology could exist and remain undetected was not the tight lower bound that had calcified into consensus. It was somewhere between 2 and 6 times smaller than that bound, depending on the topology type. What this means practically: a universe with a fundamental domain considerably smaller than the observable universe, small enough that we might, in principle, be able to detect it with better methods, had not actually been ruled out. It had been ruled out for specific orientations and specific search methods. The broader claim of exclusion had been overstated, not through dishonesty, but through the normal process of a result becoming more confident in the telling than in the original work. Many topologies previously filed as excluded are back in consideration. The corridor of possible cosmic shapes, which had seemed to narrow to a thin line, has reopened into something considerably wider. I find this more interesting than a null result would have been. A clean null result, topology genuinely ruled out across all viable scales, would be a conclusion, closed. This is an open question with a recently widened opening. That's a different kind of thing. More uncomfortable, maybe, but more alive. The Hall of Mirrors analogy gets used for this, and it earns its place up to a point. In a Hall of Mirrors, a finite space produces the illusion of infinite extent. You see yourself repeated, the room repeated, in every direction, and if you didn't know you were in a mirrored room, you might believe the space went on forever. A topologically non-trivial universe does something similar. A finite space with matched boundaries produces multiple images of every galaxy, the light having travelled around the topology in different ways to reach you from different directions. If the copies are far enough apart, if the topology is large enough, you'd never know the images were copies. You'd catalogue them as separate galaxies. But the mirror analogy misleads on one thing. In a hall of mirrors, the images are obviously images. The angles are wrong, the distances are symmetric, the repetition is visible. In a large topology, the copies would be of different ages. The light from the same galaxy reaching you via different paths around the topology would have travelled different distances, meaning it would show you the galaxy at different points in its history. The images wouldn't be identical. They'd be the same object at different times, and identifying them as the same object would require either recognizing the structural similarity across billions of years of evolution or finding the matching circles in the CMB, the prior signal, the older map. This is why the CMB is the right place to look. It's the oldest, largest scale signal available, and it's why the search, even with its loosened constraints, is genuinely hard. The patterns you're looking for could be there and simply require better methods than the ones used so far. So what does the topology tell us? Not much yet. The CMB hasn't handed us the receipt. The matched circles haven't appeared. The topology, if it's there, if it's a thing the universe has, is either larger than our instruments can currently see, or oriented in a way that prior searches missed, or genuinely absent. All three remain possible. The measurements don't prefer one cleanly over the others. What the topology doesn't tell us is perhaps more precisely stated. It doesn't tell us the universe is infinite. The non-detection of matched circles is not evidence for infinite flat space. It's evidence that any topology that exists is large or cleverly oriented or both. The assumption that the universe is simply connected and infinite, which had been gaining something like consensus weight from the absence of detections, turns out to have been leaning harder on the data than the data could support. The question is open, more open than it was 3 years ago. The search continues, with better methods, with more careful claims about what a non-detection actually means, with the appropriate humility about the distinction between not found and not there. There's a specific cognitive experience, I keep noticing it at the edges of this topic, that happens when a search fails to return a result that would close a question. The eye moves across the data, finds a candidate, examines it, discards it, moves on. Does this enough times and there's a mild fatigue to it, a low-grade resignation, the sense that the thing being searched for is either very well hidden or near not there, and distinguishing between those two is exactly the problem. The absence looks the same in both cases. Cosmologists doing topology searches sit with this professionally. Not knowing whether the universe has a shape that the data would reveal if only the methods were better, or whether the data is already telling them correctly that the shape is out beyond any horizon they'll ever probe. Both are consistent with what's observed. Both will continue to be consistent with what's observed for the foreseeable future. The universe, in other words, is not being forthcoming about this particular question, which, given everything else it's not been forthcoming about, is perhaps not surprising. But there is one more question that has been underneath all the others. Not the topology, not the geometry, the word itself, the one the original question was built around. Into. What into means or doesn't mean or needs to mean differently. That's what's left, just the word, and what happens when you actually press on it. The word is 2 letters and a vowel, and it has been inside the question this whole time doing quietly enormous work. Into. Say it enough times and it starts to sound like nothing. That's a real phenomenon, semantic satiation, the psychologists call it, the way repetition temporarily evacuates meaning from a word until it's just sound, just mouth shape, just air. Say into 15 times and for a moment it isn't a word anymore, which is strangely a useful state to approach it from, because when you bring the meaning back, when the word reassembles itself into a preposition with a job, you can catch it doing that job and ask whether the job applies here. The job into does is spatial. It encodes movement from one location toward another, with the second location being inside or bounded by something. The ball went into the box. She walked into the room. He reached into his pocket. In every case, a thing, a motion, a destination that has an inside. Into presupposes a container. That's not a subtle implication or a loose association. It's load-bearing. It's structural. The question, what is the universe expanding into, is grammatically equivalent to asking about the container the universe is moving toward the inside of. And that's the assumption, right there in the preposition, not in the physics of the question, not in the cosmology, not in anything that requires equations or measurements or decades of observation to locate. In the grammar, a container assumption encoded in 2 syllables sitting at the centre of a question that has been asked by everyone who has ever thought carefully about the universe for more than a few minutes. Prepositions do this. They are doing spatial work we mostly don't notice, like assumptions about how space works, baked into the grammar, just sitting there. English prepositions encode a specific model of space. Things are in other things, or on them, or through them, or into them. The spatial model assumed is one of objects, surfaces, interiors, exteriors, a world of bounded things with insides and outsides, a world at human scale, a world where everything that has a size is inside something larger. I looked into this briefly, whether other languages handle spatial prepositions differently, whether the container assumption is a feature of English specifically, or something deeper in human spatial cognition. The honest answer is that it seems to be deeper than any one language. The container schema, the idea that bounded regions have insides that things can be in or move into, appears cross-linguistically, seems to be one of the fundamental spatial concepts that human minds organize physical experience around, regardless of which language they're using to express it. Which means the question, what is the universe expanding into, is not an English language problem. It's a human cognition problem. The container assumption isn't sitting in the grammar because English is particularly bad at cosmology. It's sitting there because human minds evolved to navigate a world of rooms and pockets and bowls and bodies, developed spatial concepts suited to that world. And then we try to apply those concepts to a universe that is not a room, not a pocket, not a bowl, and the concepts don't fit. Now, what does into require specifically? 3 things, I think. First, an exterior. A space outside the universe into which it is expanding. Somewhere that is not universe. Currently unoccupied by the expansion, into which the expansion is pressing. Second, directionality. Expansion that has a destination, that is moving towards something, that will eventually arrive somewhere, that has a trajectory through the pre-existing medium. Third, the universe's object, something with a boundary, a surface that is the distinction between universe and not universe, an inside and an outside that are categorically different. Take these one at a time. The exterior. Is there space outside the universe? General relativity does not produce an exterior. The space-time manifold that the universe is modelled as doesn't have an outside in any mathematically meaningful sense, not because we've checked and found nothing there, but because the framework that best describes the universe's geometry doesn't include a larger space for it to be inside of. This isn't a measurement result. It's a structural feature of the theory. You can ask what's outside a 4-dimensional space-time manifold and the question doesn't have an answer, not because the answer is hidden, but because outside requires a larger manifold and there isn't one specified. Could there be one? Theoretically, some models, certain formulations of string theory, some inflationary multiverse scenarios, do posit higher dimensional spaces within which our universe exists as a lower dimensional object. A brain in the language of some of these models. Our universe is a four-dimensional surface within a higher dimensional bulk. In this case, there would be an exterior to the bulk space, but and the question, what is the universe expanding into, would technically have an answer: the bulk. But this is speculative in a way that general relativity and standard cosmology are not. It's theoretical framework stacked on theoretical framework, with no observational support and no clear path to obtaining any. Mentioning it is honest. Treating it as the answer is not. The mainstream position is no known exterior, no established framework requiring one. The universe is not an object inside a larger space, and the directionality is the expansion moving towards something, no. And this is where the explosion model from Chapter 3 comes back briefly, not as a ghost, but as a useful contrast. In an explosion, the debris has directionality. It moves outward from a centre, toward the space beyond the blast radius, into positions it didn't previously occupy. The movement is genuinely towards something, away from origin, toward new location. The expansion of the universe is not this. It has no centre, no preferred direction, no frontier. Every point is equally expanding, equally central, equally not moving toward any destination. The expansion is isotropic, the same in all directions from every vantage point, and this isotropy is precisely incompatible with directional expansion toward a destination. Into implies a direction. The expansion has none. The universe is object. Does the universe have a boundary, a surface, an outside that is categorically different from an inside? Maybe, if it's finite with a specific topology. Maybe not, if it's infinite. And if it is finite, as we discussed in the chapter on finite without boundary, it likely has no boundary in the sense into requires. A closed manifold has a total volume but no surface. No edge, no place where inside meets outside, because outside is not a geometric feature of the structure. So the universe in the most likely models either has no boundary because it is infinite, or has no boundary because it is finite and closed. In neither case does it have the kind of surface that into presupposes. 3 assumptions, 3 mismatches with the physics. Exterior, not established, possibly non-existent. Directionality, incompatible with isotropic expansion. Universe as bounded object, inconsistent with current models. All 3 required by the word into, none of them supported by the science. This is the moment. I want to be careful here, because it would be easy to let this land as a dismissal of the question, well, you were just confused about grammar the whole time, goodbye. And that would be wrong in a way that matters. The question is not confused. The question is real. The question is pointing at something genuine, the strangeness of an expansion that seems to require somewhere to expand to, the intuition that more space means space that wasn't previously there. That space that wasn't previously there must have been something else previously. That intuition is not stupid. It's the container schema being applied honestly to a situation where it almost fits. The question is real. The word into just doesn't fit the physics, which is not a failure of the person asking. It's a failure of the available language. What would the right word be? I don't know that there is one. Not in English, not in any language I know of, not coined yet. What the universe is doing when it expands is something for which human languages have not needed a word because human experience has never needed to describe it. Space producing more of itself. Distance increasing without motion. A metric changing while the objects embedded in it remain in place relative to their local neighbourhood. These are things that require equations to say precisely and approximations to say in words. The approximations all borrow from the container model because that's the model available. Maybe the right framing is not into, but as. The universe is not expanding into something, it is expanding as itself, becoming more of what it already is, which is space, which is distance, which is the medium in which everything else exists and from which there is no exterior vantage point. That's not a satisfying substitution. Expanding as itself doesn't have the grip of expanding into something. It doesn't produce the same sense of spatial orientation. But it might be more honest. It might be pointing at the actual thing, in the way that approximate words can sometimes point at a thing even when they can't hold it. The universe is expanding. Into is the wrong word. What the right word is, whether language gets there eventually, whether the physics eventually produces a vocabulary adequate to it, whether this is permanently a thing that equations describe and words only gesture at, that's genuinely open. Not as a failure, as a frontier. And the question that opened all of this, the one asked at a dinner table, in a car lying in the dark looking at a ceiling, that question was never a bad question. It was a human question, a question produced by a mind trying to apply its best tools to a situation its best tools weren't built for. That's not something to correct, that's something to sit with. The tools straining at the edge of their range, the question pointing past the edge of what the tools can reach, your back at the ceiling, or the dark behind your eyelids, or the particular velantat of wherever you are right now, the specific weight of your own stillness. The body has its own kind of knowledge at this hour. It knows you've been somewhere, moved through something, and it's ready to stop. The mind takes longer. It's still carrying things. That's fine. There's no requirement to set them down. The question that started all of this, the one asked at a dinner table or in a car or exactly where you are now, hasn't been answered. Not cleanly. Not in the way that satisfies the part of the brain that wants a fact it can file and move on from. What happened instead is something different. The question was turned over. The word at the centre of it, into, was taken apart and found to be doing work that the physics doesn't support. The container assumption was named. The explosion image was set down. The geometry was examined in 3 forms, none of them comfortable, all of them real. The light in transit was acknowledged. The topology was left open because open is where it actually is. That's not a failure to answer. That's what the answer looks like for this question. Some questions are dissolved rather than solved. Some questions, when examined closely enough, reveal that what they were really asking was something slightly different than their grammar suggested, something the physics addresses, just not in the form the question expected. This was one of those. Here is what is true, right now, as you lie there. The universe is larger than it was when this sentence started. Not metaphorically, not as a way of gesturing at vastness. Actually, measurably, in the most literal sense available. The distance between every gravitationally unbound pair of objects in the universe is greater now than it was a moment ago. The space between the Milky Way and the galaxies of the Virgo cluster is greater. The space between galaxy clusters at the edge of the observable universe is greater. It has been getting greater continuously, without pause, for 13.8 billion years, and it is getting greater right now, tonight, while you're doing nothing more than lying still and breathing. The universe is it's doing this right now, this expansion thing while you're lying there. Not out there somewhere in the news, not in a laboratory, not in a telescope image. Here, the space between your ceiling and the nearest galaxy cluster is quietly, patiently accumulating more of itself. The expansion doesn't know about you. It doesn't require your attention or your understanding or your willingness to find it meaningful. It just continues. Patient the way something is patient when it has no concept of waiting. And it is not expanding into anything. That sentence used to feel like an incomplete answer. After everything this script has moved through, the geometry, the topology, the word itself, The history of the measurements, the light that will never arrive, it feels more like a complete one. Not complete in the sense of satisfying every version of the question, complete in the sense of accurate. The universe is not expanding into anything because anything requires an outside and the universe does not have one. Not in any framework the physics provides, not in any model that matches what the instruments show. What it's doing instead is being more of itself than it was. Which sounds circular and probably is, a little, but it's also the closest language gets to what the equations actually say. Space is increasing, distance is increasing, the metric, the mathematical object that assigns lengths to separations, is changing, and the change propagates everywhere simultaneously. And there is no exterior reference frame from which this change could be measured against a background. There is no background. There is only the changing itself. The light that left before we were here is still going. Right now, somewhere in the expanding dark, photons that were emitted before the Earth existed are in transit toward the regions of the universe they will never reach, carrying information about moments that are completely finished, moving faithfully through a geometry that is working against them, not against them with any intention, just the expansion doing what the expansion does, and the light doing what light does, and the two of them in a relationship that doesn't resolve into a rival. I find I can hold that without it feeling sad exactly, adjacent to sad. The irreversibility of it has a specific texture, but it's the texture of something true rather than something tragic. True things that are unreachable have that quality. The distance is real and the light is real, and the fact that they can't complete each other doesn't diminish either of them. There's a version of you from earlier tonight, before this, whenever earlier was, who would have said the universe is expanding and meant something like things flying outward into a dark surrounding void. That version isn't wrong in the way that wrong feels like a correction. It's just, it was holding an image that doesn't quite fit the thing. And the image has been gently, slowly replaced by something that has fewer comfortable edges, that doesn't offer a container or a center or an outside you could hypothetically press your hand against. Something stranger, and in its strangeness somehow more settled. The universe doesn't need a container. It doesn't need an outseat. It is the thing that contains, and the thing that expands, and the thing in which the question was asked, and the thing the question was about. It is all of that simultaneously, and it is doing it without edges, without external reference, without anywhere else to be. That's what's true. That's what the instruments say, and what the mathematics says, and what you're floating inside of right now, heavy and still, in the ordinary dark of wherever you are. This project runs on something small and stubborn. No network, no budget. Just this. Alison, who's been here from the beginning and whose steadiness I think about more than she knows. Matthew M. and Brian Winter, who came in as co-creators and changed what this felt like to make. And everyone else on Patreon who decided this was worth keeping going. You're the reason the next one gets made. If you've found something here, something worth a quiet night and a strange question about the shape of the universe, consider supporting the work at Patreon. The link is in the description. This is self-funded, and it stays that way because of people who think that slow, careful, honest science content is worth having. Thank you, genuinely. The question broke the room once, at a dinner table in a car, at a ceiling just like this one, and now it's been carried through 13 chapters and it hasn't been put down so much as redistributed, spread out, examined, some of its weight transferred to the physics and the geometry and the preposition that didn't fit, some of it still here, undissolved, still asking. That's where it should be, not resolved and not dismissed. Carried forward into sleep and into whatever thinking happens in the hours before morning, those slow half-formed thoughts that don't have the structure of argument but sometimes that have the texture of understanding. The universe is larger now than when this sentence started. You're inside it, you always were, and just the fact of being inside, Something this large and this strange and this patient, something that has no outside and needs none, is, tonight, enough.